Okay, question 10, big one, broken up into lots of small parts. So Rory runs a distance of 45 meters in 12.5 seconds. He starts from rest and accelerates to a speed of 4 meters per second. He runs the remaining distance at 4 meters per second. Rory proposes a model in which the acceleration is constant until time t seconds. Part 1 wants us to sketch the velocity time graph for Rory's run using this model. Okay, so let's get some axes. Okay, so going up the side then, we have velocity in meters per second. Along the bottom, we have time in seconds. Now, for the first part of his run, he accelerates with a constant acceleration to a speed of 4 meters per second. So let's do that. Now we know that this is at time t seconds, and his velocity is now 4. Now we know for the rest of his run, his velocity stays at 4 meters per second. So that's just a horizontal line going across like that. Now we know the whole run takes him 12.5 seconds. So there is our graph. Okay, then part 2 wants us to calculate t. So we know the total distance he ran. So total distance is 45 meters. Now, on a velocity time graph, the area under the graph represents the distance travelled. So, we've got a trapezium here. Could break it into a rectangle and a triangle. I'm just going to do it as a trapezium. So the trapezium has a height of 4. It has a base of 12.5. And its top length is 12.5 minus t. Now, just as a reminder, the area of a trapezium, where you know the height, the top is A, bottom is B, area is height times A plus B all over 2. So, we know then that for lots of 12.5 minus t, add 12.5, all over 2 is equal to 45. Now, on top, 4 divided by 2 is 2, so we got 2 times 12.5 at 12.5 is 25, minus t is equal to 45, so 50 minus 2t is equal to 45, add 2t, subtract 45, 5 is equal to 2t, so t is 2.5 seconds. Cool. And part 3 wants us to find an expression for Rory's displacement after little t seconds for little t greater than or equal to 0 and less than or equal to big T. Okay, so this is Suvat, which we are given. Now, the equation that I'm going to use is S is ut add 1/2 at squared. So, we know that u is equal to 0. We know, or we can work out the acceleration. So, the acceleration we know it got to 4 meters a second in 2.5 seconds. So its acceleration is 4 over 2.5, which is 1.6. So, we know then that his displacement is ut, which is 0, add 1/2 of 1.6, so 0.8 times t squared. Cool. Okay, part 4, we want to use the model to find the time taken for Rory to run the first 4 meters. So, for that then, we need S to equal 4, which means then that 4 is equal to 0.8 t squared divided by 0.8. 5 is t squared. Square root t is root 5 seconds, which is 3 sig figs, 2.24 seconds. Cool. Okay, then Rory proposes a refined model in which the velocity during the acceleration phase is a quadratic function of t. Graph of Rory's quadratic goes through 0, 0 and has its maximum point at S4. In this model, the acceleration phase lasts until time s seconds, after which the velocity is constant. Part 5 wants us to sketch a velocity time graph that represents Rory's run using his refined model. Okay, So, what this is doing then is replacing the straight line for his constant acceleration with a curve to show variable acceleration. So it's much more realistic. So we know then that we go through 0, 0, then we come up to a maximum point of s seconds and a velocity of 4. So after that, we then know he runs with a constant velocity. So again, we got velocity, side, time along the bottom. So that's how it's now going to look. Okay, then part 6 wants us to state with a reason whether s is greater than t or less than t. You are not required to calculate the value of s. Okay, so this comes down really to the fact that the area under the graph has to be 45. So let's think about it. First of all, if s was equal to t, then we know the graph would look something like that. Now we can see the area would be greater than it originally was, so that can't be true. Now, if s was less than t, it's going to be even worse, so we're going to accelerate up to our maximum there, and then carry on at 4 going across. So that didn't go very well. Let's try that again. So say we peak there, and then we're running at 4, so that's even worse. There's even more area. So for it to balance out, s must be greater than t. So then the curve has some area above the line, but the line has some area above the curve. So it would balance out. So s must be greater than t. Cool.